n, so each one has the same probability. So probability of each one is 1 over n, for example, proportional to n, if n is the number of the ensemble. How I can write that? I can say that for microcanonical ensemble, the matrix of the row is diagonal. So the matrix will be diagonal. I mean, if I write the matrix, it will be just row 1, row 2, row 3. And here you will have all the 0, 0, 0, 0. This is the representation matrix for the microcanonical ensemble. If the number of the accessible state, you remember the accessible state, we should call it by gamma or something like that, not n. If gamma is the number of the accessible state or density of the state or whatever you want to say, so 1 over gamma will be seated here as the diagonal element. You will not work with that, so that's not very important because the ensemble which we work is with canonical. So canonical is the one which we needed to work on that. So in the book there is a proof of the quotient rho square equal to rho 4 just for microcanonical. This is very, I'm not interested in this proof, but our proof was more general. The second one is the important is canonical. So actually this is the one that you needed to know. How to write the rho for the canonical. Rho and m will be rho and delta and m. But the probability is not the same. You know, probability of the finding of each one is proportional to the E minus beta n. Huh? Proportional. So if you want to make it this exact, you need to write that. And you know how to find the C. C was 1 over sigma E minus beta E n. So the rho and m element is just E minus beta E n delta. This is not. It's again back to the. It again back to the one which we before studied. So I want to make it this matrix. How I can write it this matrix form? Because if you want again use the E minus, what is the benefit of the matrix form? This is not only the other representation. It's very important. You will see that. Sometimes they give you Hamiltonian and you cannot find En. You remember it was my starting point in this chapter. I told you in many cases you cannot find the En. So what you do? Well, how you can find the partition function? The only way is the matrix way. The only way. I know that if you have the En, you can raise here and find that. Yeah, but if you have just 2 energy levels, or if you have an exact value for En. But in many cases you don't have the exact value. So what I can do is that I need to be very careful. I have a set of the function, yes, phi n. Or I can write this phi n anyway, how you want in the Dirac notation. You remember I told you that the psi star d tau is 1. Of course, if the wave function is normalized, and it's translated to the sigma and chi t squared equal to 1. I want to introduce to you an object, which this object work for you like 1, but this is not the real one. So we keep it that like our proof, and I will continue. I need more information for quantum mechanics. If you have the basics of the function like that, like the eigenstate of the particle in the box, like eigenstate of the particle in harmonic oscillator matrix, I introduced to you some things which I told you. This is not the one, but it's actually the operators which works like 1. But this is, we call it unit operator, unity operator. This is the matrix, the unit matrix, you know, 1, 1, 1, 1, 1, 1, 1, 0, 0. But you don't see that here. You don't see that this will be 1, 1, 1, 1, huh? This is very important. If I put this is 1, huh? So I put it here, and you will see that anything will be changed just by putting this 1 here. How you can be sure that this is 1? If I have a function, I call it psycho. This is a wave function. If I can show you that 1 over psycho is psycho, you'll be sure, huh? So to be sure that this is 1, I need to prove that 1 over psycho is psycho or not. Let me to substitute the 1 here. 1 over psycho will be sigma n phi n phi n r m ka phi m. Again, be careful because there is an index n, and I cannot write this with the same index. So I use it m. And let me to just make the order of this index a little bit different. Like that. Are you familiar with this and this? Do you know which one is important, which one is the essential in quantum mechanics, and which one is the auxiliary one? I mean, quantum mechanics started by this, ket. Quantum mechanics start by ket. Ket are the vector like Kalman vector. Okay? And Bera are Bera. This is the quantum mechanics is made by the kets. Never made it by the Bera. This is the complex conjugate of that. I mean, if you want to talk that, so you need it also to consider they are different things, objects. And this element is nothing. This element put it to that, it's just a matrix. 1 to 1, 1 to 2, 2 to 2. Yes, 2 to 1, 2 to 2, n to 1, n to 2. But if I write this first and put this next, what happens? It will be number. If I put this here, will be phi 1 to phi 1 plus phi 2 to phi 2, phi n to phi, the normal product. So it will be a scalar number. It will be a scalar. This, what I write here, is not the scalar. This is a matrix. You see that? This is a matrix. If I write it that, it will be like phi 1, for example, phi 1 star, phi 1, phi 2 star, and phi 2, phi 1 star, and phi 2, phi 2 star, and like that. Anyway. If I write phi and phi m, what happened? I'm here now. I just replace it. Phi and phi m is delta n m because the wave function are orthogonal, as we told you before. several times. So this will be reduced as sigma to 1 just. What is that? Sigma n Rn cos phi n. What is that? This is psi. So this element is real matrix. It doesn't look like the matrix. What is matrix? Is a modern representation of the matrix. Modern representation in terms of the barometer. And we need that. We need that exactly here. What we needed is exactly this unit operator here. So are you sure now? Are you believe that if I want to make everything matrix, you cannot do something with that? This is a number, huh? Number. This is the matrix. Instead of the delta 1 1 1 1 1 1 1 0 0, you can put it this matrix now. And you know that this is from the before. You know that this is, we call it partition function. Huh? And I replaced this here. Look at that, what happened is that I can replace this here. Be very careful, never act anything on the cat. Do everything on the barrel. What does it mean? This is a number, huh? Keep it always with the barrel. You need many times to, several years actually, to understand the importance of the each things which I mentioned here. Maybe some of them looks like just because the other difference, you know, the physics and the math difference with the many other type of the knowledge of the human is like that exactly. We are working on the exact science, so there is no things which we say this. We need to exactly say. So when I say that it should be here, because if not here, all the structure will fall. So we working on exact science. How I can make it is more beautiful? What is the En? You know that the En was the wave, is the energy for the Hamiltonian if you have a phi n. Huh? So exponential looks like like the original edge. So let me just very softly I write that like this. Huh? Yes? And you know what is that? This is the matrix of the, look what we do. And now I can relax this. So look, there is no any n here, huh? Can I put this outside? I put this outside. And I have this, huh? What is that? You know, we call this one, huh? This is one, and one goes to. So I want to say that rho is minus beta h, and what is that? This is actually trace E minus beta h, because you know Qn beta is sigma E minus beta En, and this is sigma n. Look, phi n E minus beta h phi n. It means that sigma n E minus beta h n. This is the trace. So this is that was the question which today I was planning to say to you. One of the questions. The matrix representation of the rho. You know, it's this one is very useful and very strange things. When you need it, you put it here, huh? And here you again you relax at that. Because it's 1, so 1 is 1. 1 you don't need it. But it's not normal 1. There is something here which maybe you didn't see that before, is when the Hamiltonians sit in the exponential, what do you need to do when Hamiltonians sit in the exponential? What does it mean? You have a Hamiltonian of momentum, for example, energy, potential energy, kinetic energy, anything. So what is the definition of the exponential operators? So keep it this equation, the rho is e exponential minus beta h, and I wanted to just few minutes talk about the exponential of the Hamiltonian, and we will close this lecture. And next lecture will be about to solve some examples. I had planned to solve this lecture, but I found something more interesting to say. So next lecture I will solve some example for you, like the electron in external magnetic field, and harmonic oscillator and particle in the box. So this quantity is very interesting. This is a function of the any operator. For example, Hamiltonian can be the kinetic energy. So exponential of that is very strange, because momentum is minus IH bar gradient, if you write in three dimensions. Also, you can have a different type of Hamiltonian, like I don't know, any type of the Hamiltonian, I gamma slash minus m. You never say that. This is the Hamiltonian for the fermion electron. Relativistic Hamiltonian. Of course, working with this Hamiltonian for electron, direct Hamiltonian. Working with such Hamiltonian are different from that. Here you have this called the Dirac matrix, for example. So actually, this kind of Hamiltonian is completely different from this Hamiltonian. This is a non-relativistic first. Second is that it defines the state for one particle, but it doesn't define the state for one particle. You have here two types of particle, electron and positron. Always comes with two particles. And second, that is that it has a many particle interpretation. It has a single particle interpretation. And this is the starting point for the quantum field theory. This is the starting for quantum mechanics. You are working in non-relativistic. Basically, in the master program, you have to pass a course called relativistic quantum mechanics. Especially for the person who want to work in the high energy physics, like accelerator, these kind of the things, even particle physics. This is very essential, because what you know is just about the non-relativistic quantum mechanics. This is a bachelor, actually, this kind of Hamilton. Anyway, what we can do about that? Exponential of any function, if you forget about what is this function, is just the Taylor series, So you can write that, of course, but there is a many problem with this. Formally you can do that. So we call it this formal. This is a totally formally. There are many problems about this. For example, who can know that this series is converged or not? For example, you know, in mathematics, you have always to know that this is absolute x less than 1, Otherwise you cannot write this series, For example, look at that. What is that? Formally, this is infinity, because the x which is given by the 2 is bigger than that. So this is a not converge. This is diverge. Diverge, not converge. But we have these things, you know, in theoretical physics, we have several times like that. We have the things which the x is not less than 1, is greater than 1. And people develop it before a technique called renormalization. I want to, at least this word, touch your ears. So sometimes, this is not infinity actually, but there's some technique. I know this is infinity, but what does it mean? It's some numbers plus infinity. Yeah? It can be like that also. Because 1 plus 10 million is 10 million. How you can add? Or 0.5 plus 100 million is just 100 million, is 0.5. But 0.5 is not infinity, huh? The other one. So this part is the finite part, for example, the mass of the, I can tell you very exact example. For example, in field theory, for example, we try to measure